Hello everyone. Today I will try to solve the homework 3 of the ESEN 314, and this is the first question in the homework, and we will do the question B and C. So we need to check if the system is time invariant, linear, casual, or stable. So first we need to define what is stable, casual, linear, and time invariant. So first we will check the stable first. So for stable, if the input signal is bounded and then the output signal is also bounded, then it's going to be stable. So let's see. For question B, we will try to check stable. And then we have if xt is bounded. Right, this one is just assumption. And then does yt is bounded as well. So we can do like, so we know that yt is equal to cosine 5t times xt. Right, it needs to be smaller than something over here. If this one is finite, then it's going to be stable. And then we know that the property of the absolute, we can break it down, right? Cosine of t times t smaller than, and we know that the bound of cosine 5t is just from 0 to 1, right? So it's always bounded. So 5t, and the xt is bounded by mx, right? So this one is finite because cosine of 5t is bounded. Finite. Because of that, the system is stable. Right. So the next step we want to check is to check if it's casual or not. So the system is casual if it does not depend on a future input signal, like the input time in the future. So we see that our yt cosine of 5t times xt, right? So it doesn't depend on any time in the future. If we input t, we always get a result. We don't need to calculate the signal as some time like x of t plus 1 or anything. And this one just like a constant. It's not like a signal. This one is signal. So if we have something like x of t plus 1, this is casual. So this one is not casual. So we got none casual because they're not depend on the time in the future. And then the third thing we want to check is linear or not. So in order to check linear, what's the linear first? So if we got a system x1t, right, we go through this a signal x1t and go to a system s, then we got y1t, and if we got x2t, we go through a system s, we got y2t. So if we do this following, alpha x1 t plus beta x2t, and then we let the whole signal go through system S, the following should be correct. Also like alpha of y1t plus beta of y2t. If this one is whole, then the system is linear. So in order to do this, we will first plus x1t go through a system S, and then we got cosine of 5t times x1t, right? And this one equal to y1t. We got x2t, we let it go through a system S. We got cosine of 5t times x2t equal to y2t. And then we know that, and then we assume xt will equal to alpha x1t plus beta x2t. And then what we want is that we also let xt go through a system S, and then we will got cosine of 5t xt. And as we already know so far, we let xt equal this, so we can expand this one out. Equal cosine of 5t times with alpha x1t plus beta x2t. Right, and then we can distribute then. What we got is cosine alpha cosine 5t of x1t plus beta cosine 5t of x2t. And as we already know, d2 is y1t, and this one is y2t. So we will got this one at the end. So the thing is whole, right? So we got alpha x1t here plus beta x2t. If we go through a system and we got this one, so it's whole. So because of that, the system is linear. Right. And the last thing we want to check is if it's time invariant or not. So check time invariant. So in order to check time invariant, we do two things, two steps. The first step is let the signal go through a system and then shift the output, time shifting the output. And the second step is we time shifting the input first and then let it go through a system. If the two results the same, then it's gonna be time invariant. If it's different, then it will be time variant. So we will let x1t go through a system S first, then we will got y1t, right? Which equal to cosine of 5t times with x1t. And now we shift time shifting the y1t. Then what we got is cosine 5t minus 5t naught, and x1t minus t naught. So everywhere we got t, we replace t minus t naught, right? That's first step. And the second step, we do the time shifting first. And then we let it go through with system S. And we know that x2t equal to x1 t minus t naught. And we check the result 1 and 2, they are different, right? Because of that, this one is time variant because they're not equal. So we're done with the problem B, and now we try to do it on question C. So the same thing, gonna check stable. So if we let xt equal to ut, so we will get yt equal to so ut is just a unit function. Because it's a unit function, so we know that the xt is bounded by 1, right? Because a unit function. So the input is bounded. Now let's check the output if it's also bounded as well. And then using the property of the integration of unit function, we know that the result will equal to 3t, right? And this one not bounded because the time can go to infinity, so the whole system can, the yt can go to infinity as well, as t go into infinity. So this one's not bounded. Because of this, the input is bounded and the output is not bounded, so the system is not stable. So next step, we're gonna check casual. So we can see that the input signal, the output signal is depend on time up to 3t, right? Because we're gonna add every single signal from time from negative infinity up to 3t, and 3t is like in the future. Because of that is the not casual. I mean not casual because it depends on the future input. And this one actually casual, I mean. Because this one does not depend on future input, and this one depend on future. So this one in non-casual. And now we check linear. So we let x1t go through system S, then we provide y1t equal to integration of infinity to 3t of x1 tau d tau. The same thing for x2t. x2 tau d tau. And then we just repeat the step on the left hand side. We let xt equal to the combination of alpha x1t plus beta x2t. And then we let that one go through system F. And what we get is yt x tau d tau. And we replay the x tau with this one over here. And then we know that we can separate out the integration, right? So 3t of x1 tau plus beta x2 tau d tau over here as well. And then we can bring the constant outside, and this one just become alpha of y1t plus beta of y2t. Because of this, the system is linear. And then final step, we need to check time invariant. So we do the same thing on the left hand side. The first step, we got x1t go through system S. We produce y1t, which equal to integration from negative infinity to 3t of x1 tau d tau. And then we time shifting the output signal t minus t naught. So x1 of tau minus tau d tau. So second step, we got x2t equal to x1 with time shifting first, and then we let it go through the system as to produce y2t. So got x1 of tau minus tau d tau. And we'll look at this one. Oh, actually, from here, every place we have t minus, we need to replace t minus t naught, so over here gonna be 3t t minus t naught here, and they're different, right? Because they are different, so this one is time variant. Okay, so that's the solution for our first problem. Thank you for watching. There's some error in the solution, but I fixed it on the way, so I think it's good for now. Thank you for watching.